Hey, have you ever just looked at a skyscraper and wondered, how can a steel beam hold all that up when a glass window shatters from a single hit? Or, why do some things stretch and others, well, they just break? Today we're going to dive into the hidden physics that dictates why everyday materials bend, stretch, and sometimes just snap.
It really all starts with a question you've probably had since you were a kid. You pull a rubber band, it stretches out, you let go, and boom, it snaps right back. But then you take a piece of modeling clay, you squish it, and it just stays that way. What is going on there? Why are they so completely different?
Well, the secret is all about how their internal structures react to being pushed or pulled. The rubber band literally fights to get back to its original shape, while the clay, it just gives up and accepts its new form. And believe it or not, understanding these two opposite reactions is the key to pretty much everything we're about to talk about.
Now, of course, physicists have official names for these behaviors: elasticity and plasticity. And if you can get these two concepts straight in your head, you're well on your way to understanding how all materials work.
So first up is elasticity. This is the rubber band's superpower. When you apply a force, the atoms inside get knocked out of place, but there are these really strong internal restoring forces that are just itching to pull them right back into position the second you let go. Think of things like metals, quartz, and of course, rubber.
And the total opposite of that? That's plasticity. This is our piece of clay. When you squish it, those internal restoring forces, they're just not strong enough to win the fight. The material basically surrenders and permanently changes its shape. So here's the big takeaway. Every single material, when you push it or pull it, lives somewhere on this spectrum, somewhere between being perfectly elastic and perfectly plastic. And it's this simple duality that governs how it's going to behave.
But just saying something is bendy or squishy isn't going to cut it for science and engineering. To really get a handle on this stuff and actually compare materials, physicists needed a toolkit to measure these properties. And this is where two incredibly powerful ideas come in: stress and strain.
All right, first, let's tackle stress. Now, this is super important. Stress isn't the force you're putting on the object. It's the internal force the object generates to fight back against you, all spread out over its area. It's literally the material's internal fight for survival.
And this picture shows it perfectly. Stress is just that internal force divided by the area it's pushing back on. This is exactly why a sharp knife cuts so well, right? It focuses all your force onto a teeny tiny area, creating this immense, undeniable stress.
Okay, so if stress is the cause, then strain is the effect. Strain is simply the measurement of how much the material actually changes shape compared to its original size. It's a ratio that basically asks, so by what percentage did this thing stretch or shrink?
You just take the change in its length, or whatever dimension, and divide it by the original length. And since you're dividing, say, meters by meters, the units completely cancel out. Strain is just a pure number that tells us the degree of deformation. Kinda neat.
Okay, so we've got our toolkit: stress and strain. Now, let's see how they actually play out. Turns out there are really three main ways you can apply force, and each one creates its own unique kind of stress and a matching strain.
The first one is probably the one you think of right away: tensile stress. This is exactly what it sounds like. It's what happens when you pull on something, like you're stretching a wire or a rope. You're putting it under tension.
So right here, you see a force pulling on the rod, and its original length, L, gets a little bit longer by that tiny amount, delta L. The stress is the rod fighting back against that pull, and the strain is just that fractional change in its length. Simple enough?
Next up, we have volume stress, which is sometimes called hydraulic stress. This happens when a force is squishing an object evenly from all sides at once.
The absolute classic example of this is dropping something deep into the ocean. The water pressure pushes in on it from every single direction. Now, this doesn't really change the object's shape, but it does compress it, making its total volume just a little bit smaller.
And finally, we get to what I think is the coolest one: shearing stress. This isn't a direct pull or a uniform squeeze. This is a sideways or tangential force. Imagine pushing on the top of something while the bottom of it is held in place.
A perfect way to picture this is to push the top cover of a thick book or a deck of cards. The whole thing distorts, right? It goes from a rectangle to a parallelogram. That tilting, that angular distortion, that's the shearing strain. And it's caused by shearing stress. It's all about a change in shape, not a change in size. All right, we have all the pieces of the puzzle now. We know about elasticity and plasticity, and we've got our tools for measuring stress and strain. So now we can put it all together and watch the complete life story of a material as we pull on it all the way until it breaks.
And this right here is it. This is the stress-strain curve. This one graph is like a biography for any material. By plotting the stress on the vertical axis against the strain on the horizontal axis, we get to see exactly how it behaves at every single moment, from the first gentle pull to the final snap.
So let's walk through this story together. From point O to B, we're in the elastic region. It's a nice straight line. Stress is proportional to strain. If we let go anywhere in here, it bounces right back. But then it hits point B, the yield point. This is the point of no return. Past this, any stretching is permanent. We're now in the plastic region. The material starts to deform really easily now, stretching and stretching until it finally reaches point D, the fracture point. And snap, the story's over.
So you see, every material has its own totally unique stress-strain curve, its own life story. This curve and a few other key measurements basically define its mechanical personality. Is it a brittle material? Is it a ductile one? Is it stiff? It's all in there.
Let's take stiffness, for example. Physicists call this Young's modulus, and it's essentially just how steep that initial straight line on the graph is. So you can see here, steel has a really high modulus. It resists stretching like crazy, which means it's super stiff. Lead, on the other hand, has a much lower modulus, so it deforms way more easily.
And that brings us all the way back to the real world. A material's properties, its elasticity, its yield point, its stiffness, these aren't just abstract numbers on a chart. They determine everything we can build. So the next time you look at a massive structure like that, ask yourself, what kind of journey, what kind of personality must its materials have to withstand their job, day in and day out? It's a constant battle between stress and strain, and it's happening all around us all the time.